Pues ahorita la veo para encargar esto. Pero la versión es con 6 meses de intereses.
Sí. Sin intereses.
Ahorita checo.
Ustedes si no los intereses, ¿no? Deja ver acá.
Sí.
Hello, Dr. Peterson. Dr. Peterson, can I get a mic check from you?
Testing 1, 2, 3.
Good copy.
Well, if it makes you feel better, I hear you 5 by 5. Who's got birds? All right, fess up. Who's got the birds? Okay, it is time to begin. First, some housekeeping. I hope you all saw the announcement about the next homework assignment. It's been posted. It will be due 1 week from today, of course, submitted electronically. We're going to have a quiz, not a quiz. We're going to have an exam next Wednesday, not day after tomorrow, but a week from day after tomorrow. So that's like 9 days from now. We will have an exam. We're going to use Respondus as part of the proctoring system for this exam. Has anybody used Respondus yet in another class?
Negative.
Yes, I have.
And what did you think of it?
I thought it worked fine. I didn't see any problems with it, so.
Okay, for those of you that are not familiar with it, the process is that within Canvas, you will start the exam and it will require you to start what is called a lockdown browser. It's a regular browser, but it only goes to one website, and you can't run any other applications on your computer. You can't go to any other websites. If the website you're on has got a link, that link is broken. You can't use it. Excuse me. You cannot close the window. It's what it says. It's a lockdown browser. Then that's the lockdown browser. Then with that, you will use Respondus, which is an application that runs in the background. It uses your webcam to watch your face. It records the entire session, puts it on the cloud so I can see it, and it marks areas in the recording that it thinks are suspicious. And suspicious is you look away, you get up and leave the frame, somebody else comes into the frame, stuff like that. And then it's my job to look at the suspicious activity and decide whether I think it's suspicious or not. So if you haven't used it yet, I'm going to post a sample exam that requires it so that y'all can make sure you have everything working, just hunky-dory. The only thing is that you have to have a webcam. Has everybody got a webcam now?
Negative, sir. Still waiting on mine.
Did you order it?
Yes, sir.
From whom?
An eBay account.
Okay. Any idea when it will arrive?
Stand by. Let me look it up.
Hey, Professor, I have a question regarding the exam.
Sure.
So I know like exams in the past in this class, we'd had like, extra documentation to help us answer those questions.
Mm-hmm.
Will it be the same type of atmosphere? Would we print out those documents while using the Respondus browser?
No, you have to memorize all. No. My understanding is that I can put a link in that will open in a separate window as a PDF, and you can scroll through that to your heart's content, but you can't go anyplace else. So that's, yes, there is a mechanism built in to, it's not really Respondus, it's the lockdown browser, but there is a mechanism built into that which allows for reference material to be supplied. So if reference material is needed, I'll certainly do that.
Okay, thanks.
Okay. Now, your homework, you're going to have to use a reference. And I didn't supply that to you because it's homework and it's on Canvas and you got all the time in the world to look at it. But in an exam situation, things are a little bit different. Okay. Any word on when your camera is coming in?
The email says estimated delivery Thursday of this week. Hopefully I will see it by Monday.
Gee, you're not all that, you're not very supportive of Amazon or of eBay's delivery system.
The world seems to have gone haywire, sir. I'm just giving a little buffer.
Yeah, well, I buy a lot of stuff off of eBay from my shop, and I ordered a cover for an electrical connection, and it came from Australia, and it took 16 weeks to get here. In fact, it was so long that I had actually filed a complaint, and while they were reviewing my complaint, it arrived. Okay, let's start. I told you that we were done with the hard drive, but there are a couple of things that I forgot. So we are going to go back and finish up the hard drive. As soon as I switch cameras here. There we go. Okay, so we have a hard drive. And you know that the data is stored on concentric tracks on this hard drive. And of course, there's a center hub. And then we have this not physical, but logical partitioning of the platter into sectors. So this is a track. This is a sector on that track. And the amount of data that can be stored in a sector is set by the file system. It's not something that you can change. Now, everything in a computer system has to have a place to start. Now, I've emphasized that to you before. When you turn a computer on, usually the program counter is loaded with the value 0, so that the first instruction to be fetched is from address 0. There's a place to start. That instruction is usually a jump to some place that has more instructions, but who knows? But it's a place to start. Now with a hard drive, where do you start? How do you find the data? Well, let's even go back further. When you boot your computer, part of the boot process is the BIOS goes out and looks for hardware. It goes out and scans to see whether there's a mouse out there. It goes out and it scans to see whether there's a keyboard out there. It's at a monitor, et cetera, et cetera. And part of that is it looks for hard drives. And when it finds a hard drive, it sort of takes in some information about the hard drive. And what it does is it goes to head 0, track 0, sector 0, and it begins to read. That's called the boot sector. It's the very first sector physically on the drive, and it has got a lot of information. First of all, it's got information about the geometry of the drive. How many tracks are there on a surface? How many sectors are there? How many surfaces are there? All that kind of stuff, so that the operating system knows something about the drive. There's also included in here what is called a partition table. Now, I didn't talk about this, but in the early days when Microsoft was doing Windows, we had a 16-bit machine, and they took these 16 bits and they partitioned them so that there were 6 bits and 10 bits. And these 6 bits were the sector, and these 10 bits were the track. Now, a little bit of math tells you that the maximum number of tracks is, well, 1024 if you want to be really, really accurate. And the maximum number of sectors is 64. So if you multiply this times that, you come up with 65,536 sectors on a drive. That's the maximum number of sectors that you can fit in this kind of a format over here. Can you see that?
Yes, sir.
Okay, because it's behind your picture actually. So, but you don't see your pictures, do you? This is all very complicated. No. I'm old. I don't do this very much. So
I have all of our pictures on a different screen, so I can see it fine.
Okay, great. So now that's how many sectors you could have, and I believe that there were 512 bytes per sector. So that means the maximum amount of data that you could store on a drive would be, that's 2 to the 16th times 2 to the 9th, which is 2 to the, what is that, 25th. And so the maximum amount you could store on that drive was 2 to the 25th. Then, of course, as technology grew, we could cram more and more data in here. And so the number of bytes per sector increased until it reached a point where the maximum amount of data, the maximum data per drive was 32 gigabytes. That was the maximum amount that you could store on a drive using this method with whatever they came up with for the maximum sector size. And so 32 gig, you know, that was a lot back then, but it wasn't too long before drives that were capable of holding more than that were becoming available. And DOS, Microsoft's DOS just couldn't use extra space. So Microsoft came up with this idea that they would chop the drive up into what are called partitions. And a partition is a range of tracks. So you could say partition 0 was track 0 through track, I don't know, 1024 or something. And then partition 1 would take up at track 1025 and go to, you know, something else. Track 2048, I don't know, something. But the point was that these tracks right here could be seen by the operating system as a drive. And this was seen as another drive. So on this physical drive, we had what are called logical drives. And that was Microsoft's way of getting past the 32 gigabyte limit on a drive, is you just chop it up into logical drives. And that information was kept in the partition table that's in the boot sector. It told the operating system whether there were any partitions or not. You don't have to partition a drive nowadays, but a lot of people still do because they like having multiple drives. So in the boot sector, you've got the geometry, you've got the partition table, and finally, there is a small amount of code in there, or a small amount of space, where a little code routine could be run. So when this drive is found and the operating system is reading this sector, if there is code here, then the operating system will run that code, the theory being that that's part of the initialization of the drive. But you always have to have a place to start. So you start at track 0, sector 0, head 0. You read that first sector, that's the boot sector. Then the next sector is going to be sort of the introduction or the header for the first partition. Now, it may be the only partition, but it's the first partition. And it then tells you things about this logical drive. This is stuff about the physical drive over here. And then this tells the operating system about this partition, the logical drive. And then finally, you get to the actual data. Now, that's from a hardware point of view, how you get started. From a logical point of view, or from the operating system's point of view, whenever you're looking for something on the drive, you have to know where to start. And the place that the file system starts is called, anybody want to guess? What's it called? It's the root directory. That's the beginning of all searches in a file system, is the root directory. Now, the directory, as you know, is just a file. It's a file that is very constrained as to what it can contain, because it only contains entries associated with files, or it contains entries, entries associated with files. One of those files might be a subdirectory, but I guess the directory doesn't have to know that. So we start at the root directory. Now the root directory is on track 0, or at least a link to it is on track 0. So beginning with the sector, or beginning with head 0, track 0, sector 0, you can pull off enough information to know about the hardware characteristics of the drive. Then you can pull off enough information to know about the logical characteristics of the drive. And then you get the root directory. And the root directory does not have a parent directory. It is the basis for all searches. And from there, you go to a subdirectory, to another subdirectory, to another subdirectory, and eventually you get to the actual file that you're looking for. And as you know, the location of a file is what we call a path. And the path begins with the drive. This is a local path, obviously, not a network path. And then you've got this colon, C colon says, okay, what follows over here is in the root directory of the C drive. And so we have a directory, and then we might have another directory. Et cetera, et cetera, et cetera, until you get to the file. These are actually periods, they're not. But the path is that right there. That's the path. That's what the file system uses to find your file. And then this is the entry in the last directory, or the parent directory of the file. So the path gets us to the parent directory of the file. That's the last directory in the path. And then from that directory, we can find the file entry in the directory file. And then from that entry, we can find the list of clusters that are, the list of clusters are stored in that entry. And from that list of clusters, we can then find the actual data on the physical hard drive. Okay, I think that's everything that I wanted to say about files, about hard drives. Anybody got a question? Okay, well, yeah, somebody was making noise. I want to go back now and look at the PowerPoint that we went through earlier. We had gotten to this point in talking about virtual addressing, and we paused then to talk about disk drives. So we have a master page table. Every process has a master page table. And that master page table points to locations either in memory or in a swap file of where the page table that is required to translate this address, where that page table is located. If it's in memory, we continue with the translation. If it's not in memory, then we call the pager to bring it into a frame, and we restart the process then the next time a time slot rolls around, and then we find it. So this is the mechanism that a task uses to translate a page number into a frame number. Now, now that we have multiple users, though, what am I doing here? There we go. Okay, now we already know about the process table. This is the process table. It contains information about every task that is waiting to use the CPU. It's got, you know, lots of stuff in it, but primarily what we've been interested in up to this point is the status of the process. Is the process ready to run? Is the process IO bound? Is the process currently running? That information is kept in here. But another piece of information that's kept in here is the location of the master page table for this process. Now, let's go back, all the way back to here, the page table. Because we have a page table that tells us whether the page is in memory or if not, where it is on disk. Because we have that information in the page table, we can swap out pages back and forth between the swap file and physical memory. We wouldn't be able to do that if we didn't keep track of where the things were. That's how come we can page frames or page pages. And the same is true over here. We can page the page tables only because we're keeping track of where they are. Are they in memory or are they in the swap file? And now we can go over here and we can say, since we're keeping track of whether the master page table is in memory or on disk, we can swap page the master page table. And so really all of this stuff over here can be paged at the operating system's convenience. So when a new task gets the CPU, part of what the task manager has to do when it loads the context of the CPU is it's got to load the master page table for that process. If it's not already in memory, it's got to load the master page table. It reloads the working set. It reloads some page tables over here. And so you get the same virtual address environment, translation environment that you had when you were swapped out. Now, the process table is never swapped. That has to remain in memory because it's associated with more than just one task. All of this stuff over here is associated with a single task. And when we swap tasks, we get a brand new master page table for that task and its page tables. And of course, its working set has been rebuilt. So the process table allows us to page out the master page table. So now, of course, the next question is, well, we know how to find the master page table because the process table tells us. We know where to find the page table because the master page table tells us. How do we know where to find the process table? Well, as I clicked the button too early, but anyway, there are two registers in the CPU. One of them is called the global status register, and that's this one up here. And notice that it has a process table address. This is the beginning address of the process table. Dang it, why do I keep doing that? I didn't even know it would do that. Go away. And this process status register down here, this belongs, well, I don't want to say, the information in this register is unique to the task that is currently running. The global status register up here, this guy does not get changed, at least not completely. There may be things up there that change as processes change, but you can think of this as sort of static. It always points to the beginning of the process table. The process status register, the lower one, has new information put in it each time the process is swapped. And one of the pieces of information that is put in there is the process ID. So when the task manager finds a new task to run, part of task swapping is to take information from the process table about this task and put it in this process status register. And notice one of those pieces of information is the process ID. That is the location in here where this process is found. That means that the process ID plus the process table's beginning address, when they're added together, point to the entry that describes the task that's going to be using the CPU. And then the free information can then be used to rebuild all of this other stuff. So this is sort of the complete virtual address translation mechanism. Everything is locatable basically because of this register right here, the global status register. That's the beginning point. And that is loaded at boot time when the operating system builds the process table. Any questions about that? No.
Yes, sir.
Yes,
The
speak.
the PowerPoints you have up here, is that available on Canvas?
Yeah, it's in the miscellaneous module of the homepage. Everything that I put up that's pre-written, you know, that's the PDFs and everything I put up, everything is on Canvas.
I found it. Thank you.
Any other questions? Okay, well, hold on to your seats because there's one more addition. That's a cache.
Oh my God.
Yeah. We actually cache these virtual address translations to make it even faster. So it works just like any cache. Every time you start to, or every time you translate a virtual address, the cache looks to see whether it has that page number. If it does, it supplies the frame number and the virtual address translation is canceled. If the cache does not have the virtual page, then the virtual address translation mechanism is allowed to complete. And when it's complete, the cache then stores that frame number, thinking that going to use it, you know, going to need it pretty soon. If you guys are trying to talk to me using the chat, I'm afraid you're going to have to be a little more explicit because I don't get abbreviations. Okay, remember, you're talking to a fossil here.
How
But
old
most-
are you, sir?
How old am I?
Yes, sir.
68. I will be 69 in October.
That ain't that old.
If this is a fall class, I would expect a birthday party, but y'all get off the hook.
Well, if I don't pass this class, I'll see you in the fall.
Well, it may not be me. You know, I'm part-time. I just do it when they ask me to. But I've been retired for 8 or 9 years now. And so far, there's only been one semester they didn't ask me to teach. So I must be doing something right. I don't. Okay, back to this virtual address translation cache. We can't possibly call it a virtual address translation cache because that would be too explicit. So we call it a translation look-aside buffer, TLB, translation look-aside buffer. In other words, a cache. But we call it a TLB. So that is part of the virtual address translation mechanism. And now there's nothing new. There's no red on here. You're all done. Okay, it doesn't get any more complicated than this. Does it need to be any more complicated than this? It's pretty complicated on its own. So in theory, if I told you that your working set consisted of 10 frames and I gave you their beginning addresses, and I told you that the page table began at a certain address and told you what was in the page table, and then I did the same for the master page table, and I did the same for the process table, and I did the same for the global register and the process status register and all that stuff. It's a lot of information. But if you had all that information, in theory, you could do the virtual address translation for some address that I give you in the virtual address space. You could come up with the physical address for that, and you could then come up with the value in the page that's in the frame pointed to by that physical address, and then you could use the offset to find the actual byte of data that was requested. Now, that's not something you're going to do in an exam situation. That would be, well, first of all, it'd be very painful for me to make that question because I have to come up with all that data. And believe me, that's not easy. But nonetheless, you should and could do it. All right, well, here we are. So now we've had a rather intensive look at virtual addressing. This is used by every modern operating system to give each task the illusion that it has a huge address space in which to play. Of course, it's all done by trickery and deceit, but it's done. Now, that we know how stuff is stored on the disk, and we talk about virtual addresses, we've talked about how an individual user is limited to just the data that is stored in their frames, and that's all policed by the operating system. Any address that is generated by a program is translated into a physical address, which relates to a frame owned by that program. There's just no way for a program to generate an address that references a physical piece of data in somebody else's space. It just can't happen. Now, at a higher level, in the file system, we also have this concept of a user, and that user cannot open a file unless the user has permission to open the file. So if I own the file, chances are I can open it. Now, it is possible for me to give myself no permissions at all. Read, write, and execute permission, completely denied, which means I can't open my own file. Now, sometimes people do that because they know that they're not too bright and they keep deleting files that shouldn't be deleted. And so they just block themselves from delete permission, maybe even write permission so they don't change it, but you could also delete yourself from read permission. The only way you could get to it then would be to change the permissions. Now, since you own the file, you can always change the permissions to anything you want. Nothing can stop that. In Linux, the command is chmod, C-H-M-O-D. That allows you to change the permissions for a file. In Windows, there's a dialog box in the file manager that allows you to set the permissions for files. So now we have a relatively secure system in that one user can't get to another user. But there has to be a way for the operating system to change the contents of, say, the global status register, or I forgot what it's called, the process status register. The operating system has to be able to access the process table and the master page table and page tables. The operating system has to be able to access the TLB. Since the global status register and the process status register are not in memory, they're registers, why can't a user, just a regular task, why can't a regular task go up and change the global status register to point to a bogus process register and hijack the whole system? Why can't that happen? Well, it can't happen because every CPU that is built, has a, come on, trying to do two things at once. Every CPU has an instruction set. And that instruction set, what happened? There we go. That instruction set defines what instructions the CPU can execute. So you know that if there isn't a square root instruction, you cannot execute a square root instruction because it's not there. You could, however, come up with a series of instructions that you can execute, which will calculate the square root. So there are ways around it. But the instruction set, ooh, wrong pen. That's a fat pen. The instruction set is actually partitioned. The instruction set is actually partitioned into user instructions and supervisory instructions. This is a partitioned instruction set. And in the global process table, there is a bit, and that bit defines whether the CPU is in user mode or supervisory mode. When the CPU is in supervisory mode, every instruction in the instruction set can be executed. When the CPU is in the user mode, only those instructions which are designated as user instructions can be executed. The CPU automatically transitions from user mode to supervisory mode every time the operating system is asked to do something for the task. In other words, every time a task goes into IO bound, the CPU is going to switch to supervisory mode so that the operating system routine, which takes over to handle that request from the user, that routine is operating in supervisory mode and can get to anything it wants. When the CPU is in user mode, only those instructions which users are allowed to do can be executed. But instructions are generated by the assembler or the compiler, depending on what kind of language you're using. And if you're doing this in assembly language, there's absolutely no reason you could not insert a supervisory instruction into your program. It's a valid instruction. The compiler doesn't know, or the assembler doesn't know whether you're in supervisory mode or not. So what would happen if a supervisory instruction were fetched while the machine was in user mode? Well, it would generate an interrupt. And as a result of that interrupt, it's called the illegal instruction interrupt. And as a result of that interrupt, the operating system would take over in supervisory mode, and it would decide what to do. Usually what it does is it kills your program. There's really no graceful recovery from that sort of error. So if a supervisory instruction happens to wind up in your instruction stream, your program's probably going to crash. This is a good time for you to go to Canvas and take a quiz. There is a quiz that is open on Canvas. It's a 5-minute quiz. So everybody go to Canvas, go into the quizzes, and take, I think it's quiz 4, but I'm not sure. Maybe I should go to Canvas and look.
3.
Quiz 3?
Yes, sir.
Dr. Peterson, I meant to ask, after the quiz and everyone submits the quiz, did you post like solutions for it so that way we can review it?
That's a very good question. I'm not sure. This quiz that you're taking now, I changed a lot of the options so that you could, I guess, see the answers and stuff like that. I honestly don't know. So you're telling me that the quiz that you took last time, you couldn't see any of the answers or anything. Is that right?
Actually, I
That's
haven't. Oh, okay, then yes, someone else said that was correct because I didn't review that, but I knew for this quiz, I wanted to know what the answers were because I didn't do too well on this one.
Yeah,
Okay, well,
it tells us what answers we got right and wrong, but it doesn't tell us what the right answer is if we did get it right or
Okay.
did get it wrong.
I think this one will let you see that. And I will go back and change the other one so that you can see it. On the first, is the first quiz I'd ever given on Canvas, and I wasn't exactly sure what all those choices did, and they certainly don't tell you anything about it.
Mhm.
So for this quiz, after I submitted it, it didn't show me what I got, the wrong answers that I inputted. It didn't show me what the correct ones were. Or is
Yeah.
that supposed to happen after the time?
I think,
Yeah,
I
at
think
1 p.m.
I think I've got it set up so that the correct solutions appear after 1 p.m., something like that.
Okay.
That was another setting that I could put on there, so I did. Okay, because I made the quiz due before I put those answers out, I believe. Okay, everybody done?
Yes, sir.
Well, leave us, you know, I have a problem. I don't think I can get back to Canvas without stopping this meeting as the host. So I don't remember what the questions were. If somebody told me what the questions were, I would tell you what the answers are.
I can read them to you right now, sir.
Okay, give me the first one.
The first one is list 3 values required to physically address data on the hard drive.
Okay, that's head, track, and sector.
Very good. Question 2, virtual memory translation converts page numbers into frame numbers. Or converts what it is.
Yes, it does. It converts blank into blank.
Exactly.
It converts page numbers into frame numbers. Number 3.
What is the value required by the file system to logically address data on a hard drive?
Okay, we call that a cluster.
Okay. Question 4. Consider a scheme for storing dates which uses the minimum number of bits packed into a single value.
Okay, I remember the question.
Okay.
All right, so you're told it's 22 bits long. Now, how many bits do you need to select the day of the month?
1.
5.
Well, if you only used 1 bit, you could only select one of 2 things. Aren't there more than 2 days in a month?
5
bits.
Yeah, you need to be able to select one of 31, and 5 works out real well. That's 32. So you need 5 bits to pick the day of the month. So out of those 22 bits that you're allotted, 5 of them are going to the day of the month. So that means you've only got 17 left. Okay, how many bits do you need to pick the month of the year?
4.
Sure, there are 12 months. 4 bits gives you 16. So of the 17 remaining bits, 4 of them are going to be used for the day of the month. So now you're down to 13. And how many bits do you need to decide between BC and AD?
1.
1. So now you're down to 12. That means that the field to hold the year is 12 bits long. What's the biggest number you can put in 12 bits?
4096.
Yeah, I actually accepted that answer. The actual answer is 4095. Don't forget, starts with 0. So 12 bits gives you values from 0 to 4095. So this scheme would work until the year 4095 was over.
I put in
Yeah.
4096 and it gave me it wrong.
It said you got it wrong?
Yep.
Did you put BC?
Yeah, did you put BC?
No.
It says, what is the first year for which this is valid?
It submitted it before I could type in BC.
Why? Was it the end of the time?
Yeah, it was the last 5 seconds, and it was like, it's gonna quiz is submit in 5 seconds, and I was like, oh, well, I guess I can't type anything else.
Well, in 5 seconds you could type BC. But
No, the system literally wouldn't let me type in BC. It would said your quiz
Yeah,
is
it
submitted.
brings up the prompt and it doesn't let you
Really?
answer anything. Yeah.
okay, so you have 4 minutes and 55 seconds to do the quiz. Something like that?
Yeah.
Okay. So 4095 BC is the actual correct answer. Now, one of the problems with this quiz mechanism is there's no way to give partial credit, at least that I know of. I would have loved to put in there 4096, you get, 80% of the credit. 4095 with no 80 or BC, again, you get 80, 75, 80% of the credit, but there's no way to do that. So, okay, let's see here. All right, now back to our partitioned instruction set. We talked about how the operating system, or the CPU actually, always goes into supervisory mode when you call the operating system for service. There is no instruction that says change to supervisory mode, because that would be stupid. If that were a user instruction, that means the user could change to supervisory mode anytime they wanted. And if it's not a user instruction, then you're already in supervisory mode when you execute it. So you don't need that instruction. You do, however, need an instruction that says go back to user mode. And that, of course, is well, actually, I don't think it would matter if it was a supervisory instruction or not. The supervisor executes that to go back to user mode when the user task is ready to begin. So we've got a mechanism for going from supervisory to user and from user to supervisory. Now, an interesting little story from history, when when Intel came out with their very first partitioned instruction set, I believe it was the 8286, which was a very problematic processor in many ways. But the 8286 automatically comes up in supervisory mode. And they figured, why on earth would anybody, once you're in supervisory mode, want to go back to user mode? Because they weren't thinking multitasking. And so they actually built, manufactured, and sold a processor that had no mechanism for going back to supervisory mode. I think I said that wrong. And so they actually came up with a workaround. Believe it or not, every single time you wanted to go back to supervisory mode, they did a soft reset of the processor because it boots into supervisory mode. So it was a very lengthy process. It took a lot of time to change modes. The 286 was just not the world's best machine. They made up for it when they came out with the 386. That was an incredibly stable machine, and it lasted for quite a while. And the 486 was also very stable. So in order to have a multitasking, multi-user, multitasking system, you have to have a partitioned instruction set. You just have to. Otherwise, some process is going to screw around with some other process, and everybody's going to get unhappy. So the partitioned instruction set guarantees that the operating system is in control at all times. At least that's the theory. All right. Now, we've talked about a lot of stuff that the operating system does for us. The operating system provides services that swap tasks, that the file system, of course, gives us access to the disk drive. But what about other stuff in the operating system? We've got, I need to switch cameras, but I don't know where this, there it is, switch camera. Wish I knew what that red screen was from, because I only have 2 cameras. We've got a CPU over here. And we've got memory over here. And we know about the buses that go between them. Right? But we've got a host of other devices that the CPU would like to talk to besides memory. One of them is the disk controller. So we've got the disk controller. We've got a printer, got a mouse, keyboard, all of this stuff we're going to talk about. How does the CPU talk to these things? Well, I must have hit this or something. It's not. If you get motion sickness, maybe you should look away. Okay, in the early days, what they did, now, when I say communicate with these things, each of these have some registers. The printer has a register that the data that is fed to the printer is actually addressed to a register in the printer. And there's a register in the mouse. Now, we don't write to the mouse. We can read from the mouse. If you write to the mouse, it moves by itself on the desk, and that's very disconcerting to people. We want to read and write to the disk controller and a keyboard. Each of these registers, the clock that drives the register that tells it when to store data, that clock was driven, here's the strobe for the printer's register. This is some function of the address bus. So if a certain address was on the address bus, that would generate a strobe to the printer. And of course, the data bus was always hooked up to the data inputs of that register. So the data inputs of that register basically saw all data that was running around on here, but it didn't do anything with it unless it was strobed. And the same thing with all of these. This is called memory mapping, these peripherals. We take some memory address and we assign it to that peripheral, and this peripheral, and this peripheral. Now, the upside of that is memory accessing is rather fast, and there are a lot more instructions that address memory than anything else. And you'll see what that means in a minute. The downside of memory mapping is it carves out a chunk of memory that we can't use. There can't be any physical memory that responds to those same addresses, because then we have two devices trying to drive the data bus. So there's a hole in our memory. Now, where that hole is and how big it is depends on the operating system and the way the motherboard is put together. But it's there, and it gets even worse because this function did not decode the entire address bus. It just decoded higher orders of the address bus. So it turns out that this strobe was generated when any address within a certain range was on the address bus. This range would represent the low order bits of the address bus, and the function was responding to the high order bits. So the amount of space taken out of the memory actually got pretty big, because the printer might be occupying 128, 256 addresses that can't be in memory, and the mouse is doing the same, and the disk controller is doing the same. And even though the printer may only have 3 or 4 registers, just to make this function right here simpler, the printer responds to 256 different addresses. And if all of those generate a strobe, or maybe half of them generate a strobe and the other half read this register or something like that. So a fairly large chunk of memory was taken up by memory mapping these peripherals. And back then, we didn't have a lot of memory. Well, what came along then was the idea of, let's give all of these peripheral devices their own address space. We've got the memory, it's got an address space. Let's create a second address space for these peripherals. And so that's basically what they did. This is called the memory address space, and this is called the I/O address space. Now, the I/O address space uses the same address bus, and it uses the same data bus, and it uses the same control bus, except in the control bus, there is now a bit called MEM IO. And this one bit determines whether the address that's on the address bus is destined for IO or memory. So really now, in order to decode an address, if the address bus is n bits wide, you have to take this extra bit from the control bus into account. So really, what we did was we doubled our address size by creating a second address bus, or address space. So now when the CPU wants to talk to a peripheral device, it uses an instruction which sets this bit down here to IO. And all of these devices, their address decoding logic right here uses the MEM IO bit as part of its decode. It's never going to strobe the printer unless this bit is in the IO state, and the address bus has got the proper address on it. So now, we've got a separate address space up here. We can completely fill our memory address space, and we don't have to steal any ranges of bits or bytes to put up here in the IO address space. So basically, memory instructions are load and store. We've already talked about those. So load and store. IO address instructions are in and out. In is essentially a load, but it's a load in the IO address space. Out is a store, moving data to the device, but it is in the IO address space. So depending on which instruction is executed, that determines the value on the MEMIO line in the control bus. Any questions about that? No questions. Anybody out there?
Go here.
No, sir.
Out here.
No, everybody's gone. You know, I hear these these chimes when people join and leave the meeting, and I get these chimes all during the lecture. Like maybe somebody's getting up to go to the bathroom, or get a cup of coffee or something. I certainly can't complain about that. Does that make you thirsty? But makes
We
me
know that's
wonder.
not coffee, boss.
What's that?
We know that's not coffee.
Yeah, it's not pure coffee, but all right. Well, we got a couple of minutes left. What I want to do, since we've been talking about the IO devices, is I kind of want to talk about IO devices. Did we talk about how mouse works? I don't remember talking
I
about it.
don't think so.
As far as how it maps, like where it is, I think you talked about it briefly.
Yeah,
Like a Mickey. I remember you brought it
yeah,
up.
Yeah.
I do remember that, but I do that every semester, and I can't remember whether I did it this semester or I'm remembering 1981. So yes, a mouse. I just happen to have one here. This is an optical mouse. Early mouses had a little rubber ball in the middle, and there were two axes that read the position of the rubber ball. As the ball moved, it rotated a shaft, and that shaft was attached to a disc, and the disc had slots in it. And so as it rotated, a light detector and light source pair got little pulses of light as these slots rotated around. It's called a chopper, is what this disc was called. And so by detecting the number of light pulses, you could turn that into how far it had moved in the X direction, and then the other chopper told you how far it moved in the Y direction. And those two values were put into a byte. Well, actually, there was a 16-bit X delta X and a 16-bit delta Y, and then an 8-bit button status. So these 5 bytes were sent by the mouse. This told how far it's moved in the X direction since the last time it sent a packet. And this tells how far it's moved in the Y direction since the last time it sent a packet. And this tells you which buttons are pushed. Now there's 8 bits in here, so theoretically a mouse could have 8 buttons. Now, most of you've probably never worked with a mouse with 8 buttons, but they do exist. So these 5 bytes were sent by the mouse every time it moved. And they told the mouse driver where to move the cursor on the screen. And by the larger these values were, that also meant well, not necessarily. It doesn't really mean how fast the mouse is moving. You compare these values with the last values that you had, and you can determine how fast the mouse is moving. And that becomes important because many mouse drivers have got an accelerator built in. If you move the mouse slowly, it's very precise. If you move it quickly, a small amount of mouse movement moves the cursor a great deal. So that's basically how mice work. And then the mouse driver sends an interrupt to the CPU, and it then calls the cursor driver, you know, and all that kind of stuff. So that's how a mouse works. I told you that mouse movement is measured in Mickeys, and I didn't make that up. So, okay, that's it for today. On Wednesday, we are going to continue talking about peripheral devices, and we're going to talk a little bit more about RISC versus CISC. Those are the topics for discussion on Wednesday. So, bye, y'all. Ooh, look at that, right on time.
Yeah.
We'll see you on Wednesday.
Good day, sir.
Have a good one.
Good day.